An idea that will show up a lot will be the Taylor series expansion. Sometimes functions are really complex and need to be approximated. So this isn't just for functions. This is like solutions to like differential equations and other fields and modeling. So basically we say a function is equal to the infinite sum, or however many sums you want to take, but usually it's infinite, of the derivative of centered around some point. If it's a Taylor series, it's around the point x is equal to 0, and this f to the n is the nth derivative. This is the factorial, and this is the polynomial term. So any term can be expressed as this, any function I should say. More and more terms, this becomes more and more accurate. So this is the sum from n is equal to 0 to n is equal to infinity. So if we want to do, say, e to the x, this is infinitely differentiable, and it will always give e to the x. It will never give anything different. At x is equal to 0, we plug in this e to the 0, which is just 1. So all points will be 1. So this Taylor series will become this infinite sum of this, which would look like x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus dot 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 x to the n over n factorial. So this is 1 over 1, which is this 1, plus x over 1 plus x squared over 2, x cubed over 2 times 3, 6, plus x to the 4th times 2 times 3 times 4, or 4 factorial is 6 times 4, 24. If we were to plot this for small values of x, this will be fairly close to x, e to the x. If we, obviously summed it up to infinity, it would get really, really, really close to e to the x. For example, now we can do, let's try cosine. F prime of x is equal to minus sine of x. F double prime of x is equal to minus cosine of x. And F3 triple prime of x is equal to sine of x. And so on and so forth. So this would be cosine of 0 divided by 0 factorial x to the 0 plus negative sine of 0 x to the 1 over 1 factorial plus negative cosine of 0 x squared over 2 factorial plus sine of 0 x cubed over 3 factorial. And these sine of 0 terms cancel, so we're going to only have even terms. So this is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I know we didn't do the x 4th term, but it would be this would be a positive cosine. and then cosine of 0 is going to be equal to 1, so that's how we get these terms. So then it would be like that. So it would be 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 6 factorial and then it's going to be like plus x to the 8 over 8 factorial, stuff like that. So if we were to do sine now, we could do sine using the same method. Let's say f prime then is cosine of x. F double prime is minus sine of x. F triple prime is minus cosine of x. And then the fourth term would be the sine of x, as we started with. Now when we plug our values in, we get sine of 0 over 0 factorial x to the 0 plus cosine of 0 x to the 1st over 1 factorial plus minus sine of 0 x squared over 2 factorial plus minus cosine of 0 x cubed 3 factorial plus sine of 0 x to the 4th over 4 factorial. And this follows another pattern. Remember, these terms are 0. So that's left with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus etc. etc. So this is almost very similar. Because this is going to have only even terms, cosine is an even function, and this is a odd function. Sine is odd, cosine is even. And that's the basics for e to the x. For our Taylor series. Our Taylor series for e to the x was 1 plus x squared over 2 plus ... Our cosine was 1 minus x squared plus 1 minus x squared over 2 plus x to the 4th over 24 plus ... Sine of x was x minus x cubed over 6 x cubed over 6 or 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, ... alternating between plus and minus. And that's the basics for this Taylor series. The next video I'll do the complex exponential. Thanks for watching.